right, let's go ahead and get started. So I have mentioned that we have a midterm coming up next week. So there's this homework that's due this week. There won't be a new homework being passed out. I'm going to spend a little time at the beginning of Friday's lecture talking about the structure of the test and the way that we'll manage the class. So if you have some questions, you can ask them at that time. I will be doing an optional lecture on Friday. So it's going to be material that's if you wanted to just kind of watch the first 5 minutes of it on the recording, that would work fine. I'm going to be talking about Java 8 features on Friday. Actually, I think Friday's lecture is going to be one of the most interesting lectures I'm going to give all quarter. But I'm letting you kind of know it's not going to be on the test. People always ask, it's going to be on the test. What I'm talking about today is also not going to be on the test in the sense that I'm not going to hold you to specific vocabulary and so forth. But some of the things we're going to talk about today are relevant to stuff you're going to be doing on the exam. And it's an extra topic that we want to fit in somewhere in the course. I've mentioned to you kind of this idea of best of computer science and best of object-oriented programming. This is a best of computer science topic that we used to spend a lot of time talking about sorting and searching algorithms. We already spent a little bit of time when I had the complexity lecture talking about binary search versus linear search. Today I want to talk about the other side of that, which is putting things into sorted order. One of the ways that I like to think about this is that I think it would, if I worked at a tech company and I had, say, an hour of time to do a technical interview with someone, I think an interesting thing to do with them would be to give them the following task, that I would say, over the next hour, I want you to not use the web or any books or anything that, just kind of knowledge that you have in your head. I want you to produce for me a well-behaved sorting routine. And it can be on any standard linear data structure like an array, a list, something like that. I want you to write me a well-behaved sorting routine. And it can't be that you want to call arrays.sort, because that's using someone else's well-behaved sorting routine. I want you to write a sorting routine. And I don't want you to use a structure like a tree set or something that does sorting for you. I want you to figure out the sorting. So what would you do? Yeah?
First and foremost, what type of data are we working with, strings and others?
Well, the question is what type of data. So I wouldn't want whatever you did to be too specific to the kind of data, but it's fine with me if you kind of assume you're working with integers or you assume you're working with strings or something like that. So, but I don't want you to write something that's only going to work well on that kind of data. I'd want to be able to alter it so that it worked well on other kinds of data too. That's a good question. Yeah?
Would you want it sorted like alphabetically, numerically, A to Z, Z to A?
I would want it sorted in kind of the whatever we consider the normal order for that type. So like if it's strings, alphabetically, numbers in increasing order. So that's the way I want it sorted. Yeah? Can I define well-behaved? Yes? Next? Oh, were you asking me to define well-behaved? Well, I think that what I might say at that point is the interview can be over now if you want. I mean, I'm being a little facetious, but in a way, that's what I want. I want to see what you think a well-behaved sorting routine is. And so that's part of what I want to get at is, do you have a good sense of what a well-behaved sorting routine would be? So that, I didn't mean to you on purpose. I would kind of throw it back and say that's part of the challenge, is for you to decide what makes a well-behaved sorting routine. Any suggestions on what we might do in the hour? So I want us to spend a little bit of time talking, so part of what I also do, and it could be in this context, is I'd like us to mention some of the different sorting techniques that exist. So, and if you guys have a suggestion, yeah.
So it's not very well-behaved sorting routine, but we can go through each of the lists, find the highest or find the lowest, put it in the end, and
Okay, so this is an interesting suggestion that was made. I'll repeat what you said in a slightly different way. But I mean, there's a lot of ways of thinking about this, you know, the task I've given you. I mean, like a classic way would be thinking about it's all in an array and kind of what do you do in an array. But another way that I like to think about it, because I think that gets at the fact that, I mean, you've learned about arrays. Most people in the United States don't know how to program arrays, you know, so, but, you know, anybody in the United States knows how to sort, right, just about. You know, if you give somebody, so one of the things that I'll do is I get a stack of midterms. So suppose I have 100 midterms, and I hand them to you, and I say put them into alphabetical order, you know, so sort them by name. Most people in the country could do that, even if they don't even know what an array is. So it's kind of interesting, I think, to think of it couched in those terms. So let me try to take your suggestion, thinking of it that way. So if I had my set of 100 tests, what I could do is I could look through the exams and look for the one that is alphabetically lowest, right? I mean, that would be one of the forms of what you're doing, is that, like, you know, at any given point in time, there's a test that I've seen, maybe last name starts with B, it's the best I've seen. Oh, there's someone whose last name starts with an A. Okay, I'll use that one instead. So I'm kind of always holding on to the one that is the first alphabetically that I've seen among all these various tests. That is a well-known sorting routine. I think it's an intuitive sorting routine, and it's known as selection sort. You had mentioned that you could also be looking for, say, the largest thing. You know, that's a variation of selection sort. So the idea would be, I mean, if I was going to kind of try to describe how much work is involved, you look at ... all 100 of those tests. Right? You know, it's not 100 dots, but you get the sense. You look at all n of those tests to find the one that comes first alphabetically, and you set it aside. Done. That one's done. So now I'm going to look through the ones that are left, right, are the other tests. And there's one fewer exam than there was before, so it's a little less work than it was before. I find the one, the smallest one of that, boom, I've got my second test. And then I could kind of go through all of these things, and I end up stopping one earlier than I did before. All of these things, I'm not drawing my dots very well, but I think you get the idea that this gets faster and faster and faster, you know, so that towards the very end, you know, you've got a very short pile of things to look through because you've built up a pile of things that are in that are their proper order. So the way that I would kind of describe this dot pattern is that I would say that you kind of have this n by n square of dots, and you're really doing half of them because it gets faster as you go. But if we were thinking in terms of complexity terms, if you remember that lecture I had on complexity, it's n times n, or n squared. There's an over 2, but we don't care about the over 2. We would use that big O notation to say this is an O of n squared algorithm. So my prediction for this, in terms of how much time it would take, would be that if you doubled the input size, it would take 4 times longer to run, the square. You know, that's what, so famous algorithm, selection sort, very intuitive, great answer, not what we're going to use. It's a good answer. Yeah.
Find the midpoint of your stack of midterms.
Okay.
Help everyone identify everyone with the first half of the alphabet in their last name. Put them to the first half. Everyone to the second half. Put them to the second half.
So are you kind of suggesting that I would do something like A through L versus M through Z? Something like that? You know? Save that thought. That is a very good idea that we're going to talk about. But let's save that thought for a little bit. What else might you? Yeah.
You look at the first two and then put those two in order. You look at the next two and put those two in order.
Yeah, that's great. So kind of what you're describing, I would say, is it's going to turn out to be an n squared sort as well, but it's probably the best known n squared sort. The one you're describing is one that people use in code a lot. It's called insertion sort. Insertion sort works pretty well with relatively short lists, particularly if they're partially sorted. Insertion sort works particularly well, so it's popular. So let me try to describe what I heard you saying, which is, you know, you start out with a test. You know, you got one test. It's, you know, so it's fine. Now you look at kind of a second test, and you see for these two, which one belongs first? Which of these two comes first? And you make sure that they're in that order. And then, so you know, that's you're looking at a couple of tests in order to figure that out. Then you kind of have to look potentially at 3 tests or potentially looking at 4 tests. What you do is you just slowly build up a sorted list. So like I've got, say, 10 of them, and these 10 are in sorted order. So I've got my pile of 10 that are in sorted order, 90 more to go through, and I kind of take the next one and I figure out where does it belong? Where do I have to insert it inside this sequence? So that's actually a particularly good way to sort the exams, because we're better at doing insertion than the computer is. If it's in an array, that insertion task usually involves some shifting work. So that's kind of a little more effort involved. That's why there can potentially be a fair number of dots involved. But it turns out insertion sort is going to have an n-squared pattern to it as well, that kind of towards the end there's going to be potentially n different dots, because it may be, if this was in an array and you find that the very last test belongs at the front, you'd have to shift all the other ones over by one. So you'd have to scooch everything over by one. As I said, a person with a pile of tests could do a better job, but if it's in an array, it kind of can be very expensive. So this turns out to be another one of these n by n things, but where the triangle kind of goes the other way. So it's kind of an n by n like that gets slower as it goes along, but also an n-squared sort. But a good one, intuitive, as I said, used by programmers quite a bit. Yeah?
So you can like take the array, divide it in half, and then divide each of those halves in half and go on until you have only like arrays of one length.
That's...
Combine the arrays back together one by one.
So let me ask you a couple of questions. So, well, first of all, let me say that's a great idea, and that we call that merge sort. So that's a great idea. I think that, well, let me say the following. I'll tell you that I think this is the intuitive part. Take your pile of 100 tests and divide them into 2 piles of 50. And so then if you put these 50 into sorted order, so like maybe you used insertion sort, or you just kind of put these 50 into order, and then you put these 50 into order. So suppose you did that, right? So suppose now I've got a pile of 50 that are in sorted order and another pile of 50 that are in sorted order. Then what would you do to merge the 2 piles together? Well, you just look at the test that's on top here and the test that's on top here and see which one comes first alphabetically. And if it's this one, all right, I take that test. And now I look at these 2 and which one comes next. And I kind of, well, maybe it's that test. So by going through the different piles, you can merge 2 sorted piles into one big pile. I think that idea is very intuitive. I think the thing that's not intuitive, I would not expect that if I handed a random person on the street, sort these 100 tests, I wouldn't expect them to end up with 100 piles of tests, each with 1 in them. Which is kind of what you were talking about, right? Getting down to the point where you have just single tests. I think most people would find that weird, kind of what are you doing? But my guess is you know about this, or you can kind of see the code version of this. We are going to do what you said. We're going to do it the way you described. We're going to get all the way down to piles that are 1 big. But I think that's the part of merge sort that's a little less intuitive. But this is a great idea. Merge sort's a great idea. It's the one that we're going to end up talking about. There are like 2 other sorts, maybe 3 sorts that I wanted to mention. Anybody know what bubble sort is? Well, let me do it this way. Raise your hand if you know what bubble sort is. So there's a few people in the audience. This is, I have a friend who teaches at Duke who thinks that this is like a crime against young minds, that we've taught you this horrible sorting routine called bubble sort. He hates it. Anyone want to describe what bubble sort, what would you do with that? It's easier with bubble sort, I think, to think about the array type version than the tests. Anyone want to describe? No volunteers. Some of you know, but you don't want to. Nobody? All right, I'll go ahead and describe. Bubble sort, what you do is you look at the first 2 things in the list, and if they're in the array, and if they're out of order, you switch them. Then you look at the second and third, and if they're out of order, you switch them. Then you look at these 2, and if they're out of order, you switch them. So you're always kind of looking at things that are next to each other, and if they're out of order, you switch them. When you do that all the way across, what do you end up with? Is it sorted? No. Is it closer to being sorted? I mean, you'd hope so. What ends up happening is that somewhere along the line, you're going to encounter the largest value. And so that largest value, when you hit it, it's bigger than everything else, so it's going to get switched all the way to the end. So the guarantee you have at the end is that the largest thing has been placed at the very end. So it's a little bit like selection sort in that sense. You know, it kind of gets one thing in its proper place. But it doesn't necessarily do more than that. In fact, if bubble sort was given an array where it's in reverse sorted order, then that's all it does. You know, it kind of manages to get one thing to the end, but then you still have to do everything else. So bubble sort kind of has this pattern of it has to look at n things initially, then n minus 1, n minus 2, n minus 3, and so forth. So it's an n squared sort. One of the other things that's not good about bubble sort is that I don't think it's very intuitive. I don't think people would invent bubble sort on their own. You know, my friend Owen Astrachan thinks that's the reason we should dump that one. He thinks we should teach people BOGO sort. I mean, it starts with a B, so maybe that instead of bubble sort. BOGO sort would go like this. You look at a deck of cards, and you see, are they in sorted order? No? Pick them all up. Are they in sorted order? No? Pick them all up. Are they in sorted order? Nope. Pick them all up. Well, BOGO sort is short for bogus. I mean, it's anyway, it's part of the computer science culture if you're interested. It's meant to be a joke, okay? You know, I mean, the thing that BOGO sort has going for it is at least sometimes some people laugh when they hear about BOGO sort. But that's not a very good approach. And I do want to come back to merge sort. Let me mention this idea here. Anybody know the name of a sort that we might want to think about? Yeah. Quicksort. It's got quick in its name. So, you know, quick sounds good, doesn't it? So it kind of sounds like quicksort would be a good thing to consider. I actually, if I was doing this for real, part of what I'd be doing is trying to trick people into trying to do quicksort. Because, well, merge sort and quicksort, these are kind of the two major sorts that we use when we know that we're going to be dealing with a lot of data. Now, these other sorts are O of n squared, and you can think of n squared as being n times n, right? You know, there's an n and an n. Merge sort is guaranteed to be n log n. So instead of an n times n, I mean, we still got an n, so that's expensive. But, you know, remember what we said about how log works, that, you know, we were thinking about the idea that 2 to the 10th is around 10 cubed, so that if you had 1,000 items, this sort would take 1,000 steps, and this would take 10,000 steps. If you went to 1,000,000, it would be 1,000,000,000 versus 20 million. You know, at 1 billion, it's 1 billion billions versus 30 billion. So n log n is much better than n squared. We like things that are n log n. And merge sort is guaranteed to be n log n. I have a weird analogy about merge sort versus quick sort, which is I kind of think of this, maybe it's, I just have stereotypes of different kinds of relatives, and maybe this doesn't match your family experiences at all, but I have a lot of friends who kind of will tell me about that at Thanksgiving, you know, the family gathers. There's like the reliable uncle, always shows up early, always brings some weird pink Jell-O thing that you actually love, you know, and always writes you a check for $50 at Christmas, things like that. The reliable uncle, and people ask you about this uncle of yours, he's so boring, but, you know, he's very reliable. That's merge sort. Then there's your crazy uncle. He rides a motorcycle. Doesn't bring any food at all. What can you carry on the motorcycle? Shows up late. You're all sitting around wondering, he drives so fast. Maybe he wiped out or whatever. That's quick sort. So quick sort, I mean, and that would be the temptation of people. You're like, oh, if they ask me to do a well-behaved sort, they're going to want me to do quick sort. That's a trap then. I'm kind of trapping you to think to do quick sort. Well, the thing is, quick sort done right will be n log n. So done well, quick sort will have will have the same big O, and on average will run faster. So quick sort does run faster than merge sort when done right. But quick sort can fall apart and become n squared. So if you do it not right, quick sort can be very bad. So it's a bit of a trap to try to get you to do it. It's also very hard to get the code right for quick sort. It's very easy to make mistakes for it. But basically is this idea of splitting. So the idea would be that I choose in the quicksort terminology, we pick a pivot. So we have some way of splitting this stack of tests into things that are in the first part of the alphabet and the second part of the alphabet. And then you would take the A through L and you would further break it down into two subgroups, kind of the early part of that and the later part of that. That is the quicksort approach. And that's a very good sorting routine. This is a great way to sort those tests, by the way. I tend to do things that way, A through L and M through Z. Because, well, I know quicksort's quick if you do it right. But we're going to talk about merge, about the merge sort. I have an example. So I'm doing it with numbers. This will be in the notes for today if you want to take a look at it. So I've got some array with a bunch of numbers, and it's just what was described. You split that into two smaller lists, each of them 4 long. And then you split those into lists that are 2 long. And then you split those into lists that are 1 long. So there are several splitting tasks, kind of split, 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 until you get down to things that are 1 long. Then what you do is several merging tasks. So now you kind of merge these two into a sorted list. You merge these two into a sorted list, merge, merge, and you've got 4 sorted lists. You merge these two into a sorted list, these two into a sorted list. Remember when I said if you had a pile of 50 and a pile of 50 tests? Let's do this very last one in a little more detail, because that's like having the 50 sorted here, 50 sorted here. I've got a list that's 4 long that's in sorted order, a list that's 4 long in sorted order. So let's just kind of talk about what the merging would involve. I kind of need 3 hands to do this right, but I only have 2, so bear with me. You know, I kind of keep track of what's at the beginning here, what's at the beginning here. What comes first, -3 or 18, and it's the -3. So I bring that down, and then I would compare these two, and I'd say 13 is the next one, so I'd bring that down, and I'd compare these two. 18 is the smaller one, so I'd bring that down to here. 42 and 50, it's 42 that comes next. 50 and 97, it would be 50. 53 and 97, it would be 53. 92 and 97, it would be 92. And then this one's done, you know, there's nothing more to do, so anything left over here, I would just bring down. So that's kind of that final merging task, but you have all of the in-between merging tasks as well. I'm not going to try to prove this to you, I'm going to just kind of try to appeal to your intuition, that if you think of merge sort, it has lots of steps involved, and the order in which you do them kind of depends upon how you write it, how you implement it. But this diagram shows you kind of all of the different things that are involved. And in the merge sort approach, what's going to happen is there's kind of a splitting task, a splitting task, a splitting task. You know, we kind of do various split tasks. And what I was trying to do in showing it to you this way is that at each level, there's about n amount of work to do, n things to be splitting here, n things here, n things here. I mean, we're getting more and more lists, but the total number of things involved is always the n. You know, we've always got our n things involved. So there's kind of the splitting tasks, and then there's this merge that happens on the other side. We merge things back together. And those also kind of involve n, you know, steps. The sum of all the merging that gets done is kind of n at each level. So we've got kind of a splitting thing that ends up having 3n of these tasks to do, a merging thing that leads to 3n. It's, you know, it doesn't matter that there's 2 of them. What kind of matters is 3n and thinking about 3. Where does 3 come from? Why are there 3 levels when I started with 8 things? Well, what did I do? I had n things, and then I divided it in half, I divided it in half, I divided it in half. I keep dividing n in half, n over 2, over 2, over 2, as many times as it takes to get to 1. And we've seen that before, right? How many times do you have to divide n, you know, in half? That's n is 2 to what power, and that is the log to the base 2 of n. So 3 comes from the fact that the log to the base 2 of 8 is 3. You know, 8 gets divided 3 times to get down to something of length 1. So the total amount of work that's involved here is n different levels of split, n different levels of merge as well, but they're kind of, it doesn't matter. There's just a multiple of 2 in all of that. And the number of levels, will be log n. That's why merge sort ends up being n log n. But we'll see. We'll kind of, I mean, we're going to write some code, and we'll see whether we can, how fast our code is going to end up running. But so I kind of wanted to give you an intuitive feel for why this happens. It's this, the n work that's involved is that at each of these levels I have all n things to work with, but the idea that makes it work well is the splitting idea. Split, split, split. And you're only going to have to split log n times, because dividing things in half is very powerful. It gets you very close to 1 very quickly. So 3 splitting tasks, 3 merging tasks. Okay, any questions about that before we switch? We're trying to get a job, and I've already used up most of our time, so I don't know if it's going to work. But let's see. Let me try switching to the laptop. I want us, oops, not that one. I want us to write this sorting routine. I want us to do the actual work of writing this sorting routine. And what I've chosen, because it turns out that the operations that we're going to do here don't require anything more than the use of a queue. So I'm going to use a queue, not even an array. I'm going to use a queue. And I'll do a queue of strings, kind of is what I would end up doing. So let me compile and run my version. So this program is keeping track of how much the internal sorting routine takes. So I'm going to make a gigantic queue of strings, and I'm going to sort it with our routine, and I'm going to sort it with the built-in one. How close do you think we can get? Think of how many decades now they've had to get their sorting routine to run really fast. So I don't know how fast you think that, how close we should get, but well, we'll give it a try. We'll just run it. And what it says is that ours ran in 0 seconds. Theirs ran in 0.124. So ours was super fast. We were infinitely faster. The only problem is the lists don't match. I'm not done. Let me show you why they don't match. Well, so I said, and this program I'm going to post to the calendar today too, in case you want to play with it. Look at our sorting routine. It's empty. So that's why it took 0 time, because I'm not doing anything yet, okay? So we need to fix it so that it doesn't say lists don't match. We don't win unless it says that the lists match. We got to get that to work. So what I want to do is I want us to think about how to implement the merge sort idea. The first thing that I want us to think about is how we could write a method that I'm going to call merge into. And so I'm going to imagine that I have a queue of string called results, and a queue of string called list1, and a queue of string that I'm going to call list2. So that's kind of the idea, is that I'm going to have 3 different queues that I'm working with. And I've included this here just to kind of remind us of the problem that I was showing you on that handout a second ago. But let me say in terms of preconditions and postconditions. Result is empty. So I want, that's where we're going to put the merged result. And list 1 and list 2 are sorted. So I'm going to assume that I've got a sorted list 1, a sorted list 2. Our task is to just do the merging task. So the postcondition I want is that list 1 and list 2 are empty. Values have been added to result so as to preserve sorted order. I want us to merge the 2 piles. I want us to take a pile of 50 tests that are sorted, a pile of 50 tests that are sorted, and turn it into a pile that's 100 long, that's in sorted order. So I want us to think about how to do this. So what was I doing? I was kind of, you remember, I was comparing this against this. So it's going to be some kind of a test involved here where I'm going to remove, from list 1, and else I'm going to remove from list 2. So I want us to think about that, right? Because that's what we were doing when I was talking about the merging task, and I was saying it would be good if I had 3 hands. I kind of compared this against this. So what would you want to have be true that tells you want to take the thing that's in list 1? it's a Q. You need to know how to manipulate Q's on the midterm, so it's good to review the Q's a little bit here. Anybody think of a method that would be helpful? Yeah. You want to be peeking, right? So we want to do list1.peek to see what's at the front of list 1, right? And we're going to want to do a list2.peek to see what's at the front of list 2. So there's a string, you know, there's this string and there's that string. I mean, this example was with integers, but the concept is the same. We're going to kind of do this. And what would be the relationship that would say that we want to take the one from list 1? So let's say less than. If list1.peek is less than list2.peek. So how do I move the thing that's at the front of list 1 to the end of result? Stack Q, yeah. Exactly. Yeah. So this is a good example to go over today, right? To be reminding of, oh, what are all those methods? You're going to have the cheat sheet to remind you. But yeah, this is going to be one of the things you guys will be studying, you know, to get ready for the midterm next week. Is what was that command again? That's right. With Q's, it's remove. So we would do list1 remove to take that thing that we just peeked at, and we would add it to the result. So that would kind of move something from list 1. And the corresponding operation would be result.add list2.remove. So we're going to either take something from the front of list 1 or something from the front of list 2. Let me try compiling this. And it gives an error message where it says bad operand types for binary operator less. You're not allowed to ask whether one string is less than another string. You're allowed to do this with the primitive types, like int and double and so forth. You can ask whether an int is less than an int. But with strings, you're not allowed to do this. We're going to talk about this a lot more in a later lecture, but I wanted to kind of briefly talk about it. And man, the clock is ticking, so I don't know whether we're going to finish this in time to get that job. But anyway, well, so I got to explain what's going on here. What if I had a string variable s1 that I set to be Clinton, and I'll set a string variable s2 to be Trump. Oops, that's not what I wanted. Causing me errors. Well, it'd be better if I typed better. Let's see. Let me have a semicolon there. And let me have string s3 be Trumponomics. Okay, so I've got 3 different strings. So I can't say s1 less than s2. I'm not allowed to do that, right? I'm not allowed to do that direct use of a less than. What Java does instead is that classes like the string class have a method called compare to. So you can ask one string to compare itself to another string. And the convention is that compare to returns an int. If the int is a negative int, that indicates less than. If it's a 0, that indicates equality. And if it's a greater than, that indicates a greater than relationship. So alphabetically, not necessarily politically, or what, you all have your own ideas of what you might think about that, but alphabetically, Clinton comes before Trump, right? You know, in the dictionary, you would put Clinton before Trump. So if you ask the Clinton string to compare itself to the Trump string, it is less than. You know, the Clinton string is less. And if I make that call, you see that it returns a -17. It returns a negative integer to indicate that that is so. If I had asked S1, like S2.compare itself to S1, then I'm asking the string that's bigger, and it returns a positive integer. I could show you if you compared it against itself, it would return a 0. Let me just show you that if you ask S2 to compare itself to S3, so this is 2 strings where the second string begins with the other string. Right? You know, there aren't characters in the same spot and the corresponding spot that are different between these 2 strings. And the rule there, this is also the rule they use in the dictionary, is that the shorter string comes first. So the one that has fewer characters comes first. So if you asked the Trump string to compare itself to Trumponomics, it would say it's alphabetically less, and sure enough, it returns a negative integer. So that's something we're going to need to use here. But I don't want to talk about it a lot more than I did already. But man, look at how I screwed up what I had here. I think I even deleted the code that we had here that we had written so nicely. We had list1.peek less than list2.peak. If that was true, then we were going to do that first command. Let me make a copy of this line of code so that we can see it. Where am I missing? Oh, you're right. So let's put that in here, right? Is that, yeah, for the if. So if you would have wanted to do it this way, there's a rule of thumb to use for for compare to, which is that you ask the one thing, list1.peak, to compare itself to the other thing, which is list2.peak. And if you were interested in a less than relationship, so if you would have said less than, the way we did in that line of code, you see whether it's less than 0. So that's kind of the way to get the equivalent thing. That if you were interested in seeing whether one thing was less than the other, you see whether the compare to is less than 0. That's the, if you're looking for a greater than, you'd see if it's greater than 0 and so forth. As I said, we'll revisit this later in the quarter. This will be something that will come up on the final that will make you practice, the compare to methods and so forth. But let me compile. I think I have that right, but we'll take a look just to be sure. Yeah. So that's how you deal with one thing, but obviously we're going to want this in some kind of a loop, right? So we're going to want to do this more than once. So some kind of a test that would tell us that we want to keep doing this. So this is the merging task where we're taking something from one or taking something from the other. So what do we put for the test? Yeah, sure.
While list 1 and list 2 are empty.
List 1 and list 2 are not empty. I like it. So that's kind of, I'm glad actually that you said it in English first, right? So that's what we would want to know, is that there's something to peek at. There's something over here to peek at, and there's something over there to peek at. So we kind of want to know that that's true. Well, list 1 has a method called isEmpty, and list 2 has a method called isEmpty. So we want to know that they are not empty, right? So we would want to say that it's not the case that list 1 is empty, that it's not the case that list 2 is empty, and we need the and of that. We need to know that both of those things are true, and then that your English wording was that list 1 and list 2 are not empty. Let me see if you guys agree that's what I have written here. While it's not the case that the first list is empty, and it's not the case that the second list is empty, then I'm guaranteed I've got something in each. I peek at the two lists, and I take the smaller thing. Now that doesn't finish it, right? Because what may end up happening is that one of the lists will run out, and the other list is likely to have stuff in it. So there's likely to be things in that other list that need to be transferred as well. So we're not quite done. Suppose that it was list 1 that had things in it left at the end. We ran out of things in list 2, but list 1 still has things in it. How do I write a loop that'll transfer everything from list 1 into the result? What's that? List 1 is not. Oh, yeah. So we'll say while not list1.isEmpty, we'll do what? Yeah, result.add list1.remove, right? We take, so while the first list has anything left in it, we remove from the list 1 and add it to the result. If it was the other list that had things in it, we would say, while not list2.isEmpty, we would want to say result.add list2.remove. Now we would expect that one of these loops will execute and the other will not, because one of the lists will have become empty and the other one will not be. So you'd think you might need an if-else or something to kind of say, was it the first one that we have to do or the second one? But it turns out that the while loop test itself is plenty. That what's going to end up happening, suppose that it's list 1 that actually is empty. Well, then this while loop just doesn't do anything, because it sees, well, list 1's already empty, so it doesn't do anything. It's the second loop that kicks in. And if it was the other way around, where list 2 was empty, then having this little loop here is not dangerous. I mean, it just says, oh, well, list 2's already empty, so there's nothing to transfer. So the two different loops kind of handle each of the two cases, and we don't need a special if-else or something. That should correctly transfer things from the one list or the other list. All right, any questions about that little bit of code? Let me scooch this back over. That was the merging code. All right. Well, let's think about sorting. And we have 10 minutes to get a working solution, and I wanted to talk to you about something else as well. So we don't have much time left. How can you write complicated code fast? What might be a way to get something done quick that doesn't require a lot of typing or thought if you're good at it? Recursion. Let's try to think recursively. What would be the easiest list to sort? 1 is pretty easy. Empty is also easy, but 1 is still easy. I like to think about that personally, that sometimes I feel that I'm too weird or something. I can go to an island by myself and be the only person, and I won't be weird because there's nobody to compare myself to, right? So I will be the normal thing on that. Anyway, it's a joke. All right. But I could say if list1.size is greater than 1, so if it's got at least a couple of things, then that means that there's something to do. I mean, if it's a length 1 or length 0, there's nothing to do. It's already in sorted order. All right, and the original suggestion, the way it was suggested is split, right? Split the thing in half. So let me do this. I want to know size 1. What if I was going to split this thing in half? So wouldn't I take list.size and divide it by 2? That would be how many things are going to go in the first half, kind of half of the original size. And then size 2 would be list.size over 2. Is that going to work? No, there's an odd-even issue, right? How do we fix that? There's mods and things like that. Here's an interesting trick. Take list.size and subtract size 1. Doesn't that guarantee that that the 2 add up to list.size? So that's kind of a quick way. But we could have used mod 2 or something like that if we wanted to. But what I have in mind then is that I'm going to make a queue of string that I'm going to call half1. And remember, you put the queue for the variable, but we say new linked list of string. Because when you construct these things, you use the linked list type. Queue, I got to know that on the midterm. Queue of string half2 is going to be a new linked list of string. So I'm going to make 2 queues, and then I'm going to say for int I equals 0, I less than size 1, I plus plus, half1.add, list.remove. So I'm going to take the first half of the elements and put them into half1, the first set of things. And I'm going to say for int I equals 0, I less than size 2, I plus plus, I'm going to say half2.add, list.remove. So it should be the case that list will be empty after this. In fact, this is even more complicated code than I need to write because I don't need that second one to be a for loop. It could just say while list is not empty, right? I mean, I could just, then I wouldn't have needed to compute size 2, but oh well, we already did it. So anyway, but you guys you agree that we're at a point now, the one thing that we've done is to split the list in half, to split it into 2 halves. Okay, well, it is tantalizing to notice that merge into takes a result in a list 1 and a list 2, that it takes kind of, there's 3 queues involved there, because we've got 3 queues here now. We've got a list which is empty, so that's good. So can't we just say here, merge into the now empty list, that first half and that second half? Can't we just let merge do all the work? The answer is no. Why is the answer no? What was the other precondition? That they're sorted, that list 1 and list 2 are sorted. Darn, it's not working out. We would need these things to be sorted. These things that are half the size of the original, these things that are not as large as the original, have been reduced from the original. We need them to be, they are queues that we need to have in sorted order. We need to have queues put into sorted order. If only there were a method that would put a queue into sorted order, then we could say sort half 1, sort half 2, and we'd be done. Because now the precondition is satisfied. And if you can make the leap of faith and believe that it recursively sorted the 2 halves, it should work. theoretically. Well, let's give it a try. Well, all right, maybe what did I do wrong? Not list one. Okay, yeah. Some of you might have noticed that already. Oh, is there another one? What else did I do? Haffle? Well, that's not very good. Haffle. It's like a new word that even I don't understand. All right, good. It's, well, you guys are helping. I mean, actually, maybe it's not fair that I get the job then, because but maybe you guys are slowing me down too with questions. But so maybe it's not so unfair. All right. So it told me that the lists match. It worked. It put them into sorted order. It told me that the lists match. We were 64% higher time-wise. I mean, we were within a factor of 2 in terms of how much time it took. I don't know what you guys think about that, but that's pretty good for the amount of time we've spent on this, right? And we're using queues. You're like, oh, queues are inefficient. Recursion is inefficient. I'm not learning practical stuff. We are really, really close to the built-in sorting routine, getting the time that the built-in sorting routine gets. All right, well, there's an issue of a stable sort. Let me show you this first. This is a subtlety that I think people struggle with, but let me just kind of, well, I'll show you what I'm doing in this program. So what I do is I have a whole bunch of words, 4 score and 7 years ago, and I sort this list of words 2 different times. Let me just run it and explain to you what the output is showing. So there's the original list, 4 score and 7 years ago, et cetera, et cetera, et cetera. Then what I do is I put it into alphabetical order. So a, ago, all, and, are, brought, that's alphabetical, all right? So I put the thing into alphabetical order. Now I do an extra sort where I sort by the length of the word. So I put all the 2-letter words, so the 1-letter word appears first, then the 2-letter words appear next, then the 3-letter words, then the 4-letter words, okay? So it's sorting it by the length of the word. But there are 3 2-letter words. They're all tied in a sense, right? They can be in any order whatsoever if you said sort them so that they're, so that 2-letter words, come next. It could have been in any order, but do you notice in, on, to? Do you notice something about that? It's alphabetical. It was alphabetical before I did this sort, and it's still alphabetical now. Even though, in a sense, these 3 words could be in any order whatsoever, and it would still be considered to be a correct answer, but it was not what we call a stable sort. It did not preserve the relative order of these things that, in effect, were a tie. There are a whole bunch of 3-letter words that all tied in the same sense, but what I'm saying is that these 3-letter words could have been in any order whatsoever to be a correct sort, but they were originally in alphabetical order, and this sorting preserved that alphabetical ordering. It preserved the order that it had before. That's known as a stable sort. And Java's built-in sort is a stable sort. What we wrote is not a stable sort. Quicksort, by the way, is not a stable sort, ever. But the reason that it wasn't stable is that we said if it was less than 0, if this peak was less than this one. If these 2 are equal to each other, the thing in the first part and the thing in the second part, if we want to preserve the relative order, we want to take the first one, not the second one. If you take the second one, you're switching the order of things that are considered equal. So we want less than or equal to. You want to be, if it's less than or equal to, then you would want to pull from the first list and not the second. And if I run that version of it, it says that not only does it match, but it's also stable. So knowing what a stable sort is good. And what I would have wanted someone to say for their answer, kind of the well-behaved sort, n log n and stable. That was kind of my choice. I did it with queues. I got within 60% of the quickness of what the built-in one does. And we'll do more on Friday. Oh, yeah, I'll save it for Friday. But there's a funny thing in the code here that I'll actually talk about on Friday. There's a weird little thing that I have right here in the sorting routine that we'll talk about on Friday.